Okay, distributed loads. Distributed loads. Remember what we are doing in this few classes, the previous two classes and this one and the next one, everything is getting ready to analyze equilibrium of rigid bodies. The purpose of these few classes or this module is to make you able to analyze equilibrium of rigid bodies, which means basically you have to be able to find the forces that keep a rigid body in equilibrium. For example, this beam that you have right there is a fixed support on the left. On the left. Am I pointing to the left? Hello? Anybody?
Still to the right.
Okay. So I have to get used to point to the wrong side here. Okay, so we have a support on the left. And it has, we're going to study also how to, oh, we don't have, oh, you still have half an hour. We need to analyze how to consider this support here. We're gonna do it later today. We have time. We need to find out how to deal with this kind of loads. Up to now, we have been working with concentrated loads like this. We say P load, Q load, S load. This is concentrated loads. What can you do about a load that is shown like this? It's called distributed load. So we're going to talk a little bit about what to do with those loads. That's the way we represent uniformly distributed loads in engineering. And basically, the general discussion about how to deal with this, let's draw here. Let me draw here. A general loading. Let's say you have a load, general load like that. In general, you have a load that follows any kind of function. Let's say the load W is a function of X. That means that at any different location on the X-axis, the load that is applied has a different value. You see that the load is larger in some places and smaller in others. So how can you deal with that? The idea is that you have to find an equivalent load here somewhere, an equivalent load that will be produce the same effect as the distributed load. So first thing that we have to find is that we need to find the magnitude of that force. The magnitude of that force, let's call it the resultant of the force. It has to be the same magnitude as all these force together going down. So with the way you do it is the same as we were moving, how can I say that? We need to make a summation. We have forces in the same direction, like this one, and this one, and this one, say 3, 5, 2. If I have these three forces in the same direction, I can replace these three forces by one here that is 10. It just has to be the summation of the three forces, right? That's simply logic. If you have three forces, if you want to replace that at one only resultant, we did it at the very beginning of the class when we talk about summation of forces in the same direction. You just add or do the summation, algebraic summation of the magnitudes. If there is one that is in the opposite direction, then you will have to, let's say this is 1, so you have to subtract that 1, so this will be 9, right? It's algebraic summation of forces in the same direction. But here they are not concentrated loads, so you have to do the summation doing the integral of that. And you guys are familiar with the integral. You guys studied your calculus already. So what you do is that you take a differential of the load. If I get this to move, but it's not moving. So you have your force here. X. This is your W of X. And you take like a very tiny little piece here that has a width of dx here, right? And let's say this finishes here. Let's say this is the total length that you want to analyze here, L. So you take all the force. This little band here will have an intensity of whatever is this height here, which is W of X, multiplied by the width at the base. So it's like a tiny rectangle. I'm gonna magnify it here, where the base is dx and the height is wx. And that's this wx dx is the load applied by this rectangle here going down. So this the magnitude of that force, tiny force, we can call it df, is wx dx. So if we take the summation of all those forces going down, there will be this one plus another one next to that one plus another one next to that one, and all of these little forces from x equals to 0 to x equals to L. So you are doing the integral, right? And that's how you find the summation or the resultant of all those forces will be the integral from 0 to L of Wx dx, right? That's how you find the total force going down, this F sub r, or force, resultant force. And this has the concept of base times of height, so it looks like an area. So if you can consider that as an area, so you can say this is integral from 0 to L of differential of area. So basically, you do by integral, you calculate the area under the curve that describes your load. So you are calculating this area using your integrals, and that's how you. So this force, this resultant force will be that area, and that will be the integral from 0 to L of dA, right? We are not going to do any problem with Weor's area. We are going to do just straight lines. But it's good that you know that this can be done with integrals if you have a really weird shape. And the other important concept here is that not only you need to find the magnitude of the total force, which is the area under that curve, where in the horizontal dimension you have length, right? The units of this W of X is going to tell you in units of pounds per inch or pounds per feet, or could be newtons per meter. So it's going to tell you what is the intensity of the load per unit of length. If you have more intensity, imagine that you are you have the weight of a wall. You have the floor here, and you have a wall here. This is a wall. And then the magnitude of this in your calculation of area, this is meters or feet or anything. And this is, we are not talking about anymore about the height, but how much is the weight for, if this is 1 meter, what is the weight of this for 1 meter? Let's say that this wall has a weight of 500 newtons per 1 meter, so it's 100 newtons per meter. So if the wall gets twice as high here, so the intensity of the load in this region says 500 newtons per meter. In this region here, this load is 1,000 newtons per meter. It has double the intensity per unit of length. And in a graph like this, then the intensity of newtons per meter or pounds per inch changes constantly according to a function or whatever. And now, where do you put the resultant? Where do you locate? Because the location of the resultant is very important, because the location of the force determines the moments. So you have X, you have omega, and then you have your function here, function of X, this one. Let's say this is 0, this is L. So you find the resultant here, FR, that you can find it as the integral of the area. But remember, it's not units of area, because you have length in this direction. Length, and the dimensions here are, let's say, pounds per inch or newtons per meter, force per units of length. So when you multiply force per units of length multiplied by length, force per unit of length multiplied by length, you get units of force. So that area is in units of force. This is in newtons or pounds. That area will be in units of force. And again, we were going to now find how you calculate the location. This X, let's put this bar there because it's usually called X bar. How do you find that location? So in order to find the location, we use the principle that we have been doing all this time. We have basically what we have is many forces. We have many forces here, tiny forces. Remember the little rectangle here that has a base of dx and a height of w of x. So this is a tiny force here and another one next to it and another one next to it. So many forces, many forces. So we need to find one only force. Let's put it here. Here, let's put it down here. The force R has to be at a distance x bar in such a way that you choose any point that you want. Usually you choose the origin, which is kind of the easier way to do the calculations. And you calculate the moment of all those tiny forces. You calculate that moment with respect to O. Here it will be a summation of many forces, right? You calculate that moment, and the summation of all those many forces has to be equal to the moment of the force R with respect to O. That's the condition that you apply in order to find the location of that force. How you calculate this, the moment of all the many forces? Well, you have to do it one by one, but it's infinite. So how do you express an infinite summation of stuff? You put integral. So it will be the integral of all the forces that you find when you go sweeping from 0 to L. And the magnitude of each one of those little forces is W, X, dx, right? And the distance, in order to calculate moment, let's say I'm talking about one of them here, this one, the blue one here. This one is W of X dx. All of them can be called like that. Wx of x, very general, so this equation applies to all of these forces, The lever arm of that force to calculate the moment produced by that force with respect to O is this distance that we call x. So that is very general. So multiply by x. This integral is the summation of all the moments of all those little forces that go vertical, right? That's the moment of all the forces. That moment has to be equal to the moment produced by this one, which is force times distance, which is force times distance. The distance, we call it x bar. So if we solve for x bar is equal to integral from 0 to L of Wx dx divided by Fr that we find up here a few minutes before, which is integral of dA, right? And here, over here, more up there, here. Well, integral of Wx dx is integral of dA, right? This one right here is integral of dA. So this will be equal to integral of dA times, let me put it this way, x dA divided by integral of dA. And you guys probably are familiar with that expression. You probably have seen that expression before. X equals to integral of x dA over integral of dA. This is the centroid of the area. The centroid of the area. Right? You guys probably have seen that before. If you have not seen this before, well, just believe me, but we are going to cover this in a little more detail at the end of the course. We're going to do a little very similar development as this one, and we'll do some examples about centroids of areas. But this is to say that in order to calculate the location of a distributed load, you just consider the load as an area, but it's not really units of area. In the horizontal axis, you have length, and in the vertical axis, you have length per unit of area. So you work like if for every intent and purpose, you treat that as an area, and the magnitude of the force is just the area. You calculate the area. And in the location of the force, you find the location of the center of gravity of that area, and that's where you put the force. So that will be better seen with an example. So let's go back to our example that we have here. So it says here, replace the loading by an equivalent resultant force and couple moment acting at point O. So here you have some areas. If you know the area of that figure, if you know where is the location of the center of gravity of that figure, when I say that figure, I am talking about this figure. I don't know the location of the center of gravity of that. So what you do is you divide this, you break this more complicated figure into very simple figures like this triangle here. So we have a rectangle here and a triangle here and another triangle here. So we have two triangles and one rectangle. And you replace each one of those figures by an equivalent concentrated load, because we do know how to operate concentrated loads. So we will do like this. Let's call this one 1, 2, and 3. Triangle 1. Let's call it force 1. So you treat it just as area where this is 8. The total magnitude of this force is 8, but only up to here is this 5. So it's 5 here and 3 here. 3 kilonewton meter and 5 kilonewton meter here. So the area of the triangle 1 is 1/2 of 3 kilonewton per meter times the base, which is 1.5 meters. So the force 1 will be 30 over 2 times 1.5, 2.25, and meters with meters go away. So this is kilonewtons, right? Let's go first with now the location. Where is the location? So I'm going to replace that force by a unit here that I'm going to call F1. The important thing is to know what is this distance X1. So X1 will be the distance to the center of gravity of this triangle. If you remember, the center of gravity of a triangle, if this is the base, and this is the center of gravity, this distance is b over 3, 1/3 of the base. So that would be 0.5 meters. So that's the location of that force in order to be equivalent to the triangle. Now let's do the rectangle number 2. Now we have the rectangle 2. Let's call it F2. The force 2, you calculate it as the area of this rectangle here. The area is 5, the height is 5, and the base is 1.5 plus 0.75, 2.25. So the area will be 5 kilonewtons meters times 225 meters. So the force 2 will be 225 times 5, 11.25 kilonewtons. The location, x2, the center of gravity of a rectangle is just in the middle. It's very uniform. So if the base is 225, the half of 225, so we have the force F2 just in the middle at 1.125, right? 1.125 meters. That's the location of the force. And then the other one will be the triangle 3. The triangle 3, ugly triangle. The area of the triangle 3, I call it force 3, is 1/2 of the base times the height. The base is this distance here, 4.75 meters, times the height, 5 kilonewtons meters. 5 kilonewtons meters. Meters and meters go away, and we have 2.5 times 0.75. 1 force 3 is 1.875. And the distance from here, from the origin to the location of that force, that I'm going to put it here, force 3, this distance, x3, is equal to the total distance up to the place where the triangle starts. So is 2.25 plus 1/3 of the base of the triangle. This base is 0.75. So 1/3 of that is the location of the centroid. So when you have a triangle, you know that if this is B, the location of the centroid is B over 3, right? This is probably stuff that you guys saw before. So now we have the beam that is with a fixed support here. Now we have 3 forces. One right here, F1, at 2.25. What was that? Oh, no, 0.5. It's 0.5. Another one over here, F2, at 1.125. And another one over here, F3, at, oh, what? Oh, what did I do here? Did I do that operation? I don't remember.
Did you explain X3 again?
Let's do X3 again. Let's do the whole thing here. I have to erase a little clean up here. The force F3 is the force due to this little triangle here. So that force comes in here, F3. Is the centroid of the triangle. The triangle has a base of 0.75, so the centroid right here at 1/3 of 0.75 over 3, 1/3 of the base is the location of the centroid of the triangle.
Okay, I see it.
If you have a triangle here, if this is 0.75, so if the force here in the centroid, this is B over 3. It's 1/3 or 2/3 from the vertex at the other 2B over 3, 2/3 of B. So that will be this little distance here, but we are going to calculate moments around 0.0, so I need to add all this distance from the origin, which is 1.5 plus 0.75, that's 225, right? So x3 is equal to 1.5 plus 0.75 plus 1/3 of 0.75. So x3 is equal to 2.5. I did it by in my head, but I don't trust my head anymore. After I turned 60, I stopped doing it. 0.75 plus, well, I'm not telling you my age yet, it's way over 6, 2.5. 2.5. So now they told us to replace all this loading by an equivalent force and couple moment active at 0.0. So they are basically telling us to replace these forces by just one force and one moment here. So the resultant here will be the sum of those three forces, 2.25, 11.25, and 1.875. So it will be 2.25 plus 11.25 plus 1.875, whatever that is. 2.25 plus 11.25 plus 1.875 equals to 15.375, 15.4 kilonewtons. Now the moment here is equal to the summation of the moment produced by those three forces. So it will be F1, 2.25 times the distance, which is 0.5, plus the F2, which is 11.25 times the distance, which is 1.125, plus the other force, which is 1.875 times the distance, which is 2.5. So the moment is equal to all that operation, 2.25 times 0.5 plus 11.5, 25 times 1.125 plus 1.875 times 2.5 equals 18.5 kilonewtons meters. This moment and this force, and the moment is clockwise, right? Everybody see it? The moment is clockwise. I hope everybody see it. This is the moment. Because every force that I have here, like this one going like this, with respect to 0.0, produces a rotation in this direction, right? This one produces rotation of 0.0 in this direction. And this one produces rotation in this direction. So all of them are in the same direction of rotation, so they just add up in the same sense. So that's why I added, if one of those forces produces a moment in the opposite direction, I have to subtract, right? So that will be the solution for that problem. And again, if you are trying to do your homework, you get stuck, you don't understand something, please feel free to contact me by text me to the cell phone or call me. I guess you guys are easier at texting. Just a little note, tell me, can we meet by Zoom later on this afternoon or tonight or tomorrow, and then I'll do it. I'll do it. Over the weekend, I have more flexibility. So don't be shy, please don't be shy. I really wonder why no. Basically, very few people contact me.
Professor, I have a question about the
Yes.
same thing.
Mhm.
So I just want to make sure I have this right. So for when you're determining the x distances for the center of gravity, x1, x2, x3. So for x1, you're taking 1.5 and you divide that by 3, right? And that's where you get the 0.5. Then
Yes.
for x2, you're taking 1.5 plus a 0.5, divide that by 2, and you got 1.125. But then for x3, you took 1/3 of 0.75, but you added the other two, and that part I didn't get because on the other ones it didn't seem like you added previous ones.
Yes. We are trying to find the distance from the force to the origin.
Yeah.
That's what we are doing. So, and let me see, did I do this one? The second one I did it correctly because you have, you know what, let's move this one over here so we can do it larger here down. So for this one is 1.5, 1/3 of 1.5. So you have here the 0.5, right? No problem with that one?
Right, and that one's right next to it, so I would understand why you wouldn't add anything to that.
Yeah, because it's just next to 0.0. So what we want is the distance from the line of action of this force, which is this line here, to 0.0. So it's this distance here, or 0.5. Now the other, the blue one, is in the middle of the rectangle, right? And the rectangle has a base which is 1.5 plus 0.75, which is 2.25, right? And then up to here, but half of that is 1.125, right? Up to the load that is over here. So now this one right here, this load is over here. This distance is the one that we calculate like 1/3 of 0.75, which is 0.25. But we need the distance all the way to the origin, which is here. So it's gonna be all the distance from here to here.
Okay.
From here to here. So you have to add all this.
Okay, so the first two segments, since they were kind of connected to O, you didn't really need to add an additional distance.
Right.
Oh, okay. I see.
Good.
Thank you.
All right, you're welcome.
Have a good weekend.
You too. Take care.
Get some rest.
I'll try. I need it. Thank you very much.